So we have one more problem we're going to look at in this sum and difference identity section, and the 9.2. And what we're going to do is look at tangent and the tangent function and see if we can derive an identity for tangent of alpha plus beta. And I don't think I could ask you to reproduce these steps because they're not all obvious by far, but I think it's a good, gives you good exposure to just another kind of relationship in trigonometry that just kind of gets me thinking about how all these things are interrelated. So let's try to derive an identity for tangent of alpha plus beta, the sum of two angles. Now, if you ask me how to do that, if I had never seen it before, I think I probably would initially want to say, oh, tangent is sine over cosine, so I could write this as the sine of alpha plus beta over the cosine of alpha plus beta. That much I could say. And we have some identities for both the sine and the cosine. So I could write out those expansions separately. Sine of alpha plus beta is sine of alpha, cosine beta, plus cosine alpha, sine of beta. And cosine of alpha plus beta, from my identity list that I have, I know is cosine alpha cosine beta minus sine alpha sine beta. And I think probably if it was me when I got to here, I wouldn't know what to do next. I'd probably be kind of stuck. And I know there's a trick to apply, and I've learned it, but I don't think it's obvious to think to do it. What we're going to do is we're going to divide numerator and denominator by the same quantity. So I'm actually going to have a fraction of fractions here on top. I'm going to have sine alpha cosine beta plus cosine alpha sine beta. So I'm just recopying the numerator, and I'm leaving space for it to divide by something. Then below, I'm going to recopy cosine alpha cosine beta minus sine alpha sine beta. And I'm going to divide by the same thing. As long as I divide by the same quantity above and below, I still have equivalence. And I guess I can kind of look back and see why someone thought to do this. They're trying to get tangents. So if they see sine alpha, they want to divide by cosine alpha. If they see sine beta, they want to divide by cosine beta. But why they know to divide by cosine alpha cosine beta is a little bit more mysterious to me. Same thing below. We're going to divide by cosine alpha cosine beta. So we divided by the same quantity above and below. We have a huge mess. I'm not going to write this out as a division problem, which is something, it's kind of like a principle I apply pretty religiously, but not here. I'm going to leave this as a complex fraction of fractions, and take apart both numerator and denominator into two separate fractions. Sine alpha cosine beta over the common denominator cosine alpha cosine beta plus cosine alpha sine beta over cosine alpha cosine beta. And then below, I'm going to have two fractions again, separated by a minus sign in this case. Cosine alpha cosine beta over cosine alpha cosine beta minus sine alpha sine beta over cosine alpha cosine beta. And now suddenly all these amazing things start happening, because up above I have a cosine beta, that's a cosine beta, that cancel. I'm left with sine alpha over cosine alpha plus, I have cosine alpha cancels. I have sine beta over cosine beta. Down below, in this first fraction, everything cancels. I'm left with 1 over 1. Remember, there's always 1 left behind. 1 over 1 minus. Now nothing cancels. But I can think of that as sine alpha over cosine alpha as a fraction times sine beta over cosine beta. And now there's a way we can rewrite all of this. We actually have tangents all over the place here. Sine alpha over cosine alpha is tangent alpha. Sine beta over cosine beta is tangent beta. Then we have over just 1 minus a product of two tangents, tangent alpha, tangent beta. And so to kind of sum it all up, whoops, I went off the edge. To sum it all up, tangent of alpha plus beta is equal to tangent alpha plus tangent beta. It's kind of, to me, it's kind of funny. It's almost like we get tangent of the first plus tangent of the second, but not quite, because we got to write that over 1 minus tangent of the first times tangent of the second. And you will not have to use this identity in my class, but you should have seen it. It's the sum identity for tangent. And I want to leave with just one more thought here. Can you show the difference identity for tangent? Can you show what the difference identity would be, the tangent alpha minus beta? Given the tangent of the sum, this is really easy to show, and you should be able to do it. If you replace beta here with minus beta here, minus beta here, and simplify, see if you can get tangent alpha minus tangent beta over 1 plus tangent alpha tangent beta. So I didn't actually go through the steps, but I think it's worth you trying that on your own, starting from the identity right above the tangent of the sum identity. So there's our derivation. Zoom out a little bit and get this all in one shot. And that's the end of 9.2.